بسم الله الرحمن الرحيم الصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone to the fourth class of the course. Before we start, any questions? Any urgent matters? Concerns? As far as I know, this week you can drop this course, right? So after that, you chose it, okay? So this is your last chance to make up your mind in this lecture. And also by luck, today it's a tough lecture, okay, I would say. So it's gonna be painful because I'm again. So what we did last time again to try to talk about stuff that you heard about in a different manner. Today will be similar along the same spirit. Let's start as usual with the recap of what we discussed so far. We were talking about how we can have just not a set, but more structure given to it. And we discussed three of these mathematical objects, or the three of these spaces that have more structure, okay, including the set. So the first one is the set. This is the mathematical object we're talking about. It's just a collection of items, no such structure to be considered. Then we talked about the group, and we equipped it with some sort of binary operation that would take two group elements and give you a third group element. Then we talked about vector spaces over a field, and we said that the vector spaces over a field consist of a vector space, which is just a set, so the set V, and two operations. One we call the vector addition, the other one we call scalar multiplication. And this scalar was something from the field, and the field itself is another mathematical object. The field by itself is not of interest to us, but we always talk about the vector space inside over a field. Whatever map that goes between these spaces and respects the structure that they have, we call the structure preserving map. And depending on which category we're talking about, we have different types of maps. So just the name map would map you from one set to the other. The group homomorphism takes you from one group to the other group, and it has an extra condition. It's not just a map. It needs to respect the group structure, these group operations that G and H have. A linear map between two vector spaces, V and W, for example, is also respecting these structure, this linear space structure of V and W, and it had some conditions. We're going to revise them in a bit. We use the term isomorphisms or isomorphic spaces or isomorphic sets. Isomorphic spaces, when we want to say that these two sets, so if there's a map that exists between S and T, and what extra condition do we need on this map such that S and T are the same? Then we call this, if this is the case, if F is a bijection. If we have this group homomorphism, and it's not only a group homomorphism, but it's also bijective map, then we call it a group isomorphism. And the last one, if it's in addition to being a linear map, it's also a bijective map, then we call it a linear isomorphism. Okay? And we're going to have this table, again, extended with more categories at the time. But today, for now, these are the three categories we're talking about: sets, groups, and vector spaces over field. The vector spaces are this triplet V and this vector addition, this scalar multiplication. We call this binary operation a vector addition. We call this operation that takes one element of K and one element of V and returns an element of V. We call this scalar multiplication. And we said that it should satisfy some properties we discussed last time. And we said that an element of this vector space is what we call a vector. Okay? So a vector is not just the tuple of numbers. It's just an element of this vector space. Two examples, one that we mentioned last time. We're going to elaborate again just to remind you of them. The first one is Rn, and whatever you call vector addition in Rn, and the scalar multiplication by some real number. So Rn is a vector space over the field R, and the R plus, and with the standard plus and the standard multiplication is the field we're talking about here. This is how you know how, if I give you two vectors, this is how you add them together. If I give you one number and one vector, this is how you multiply them together. And the identity element, okay, because one of the conditions that we said that V and this vector addition is an abelian group. And if you remember, one of the conditions of the abelian group is to have this identity element, that whatever we add any element, okay, to, we get the same element. If this is the vector addition, then the identity element of this group is just the zero vector. The zero vector is whatever you add it to, okay, as a vector, you get the same vector. If we extend this to m by n matrices, this is one element of this vector space. This is another element of this vector space. So in other words, this is a vector of this vector space, another vector from that vector space. We can add them together by this new operation. This is not the same operation. Okay, of course, you treat them the same, right? I'm just element-wise adding the components. But in terms of mathematics, they are not the same operation. That's why I need to define it like that. The scalar multiplication, I define it like that. The identity element of this vector space in this case is the zero matrix, right? It's the matrix that whatever you add it to any other matrix, you get the same number. Make sense so far? Okay. Then we talked about linear map. The linear map is the structure preserving map between two vector spaces. So if I have a vector space is green V and another vector space purple W, then the vector space between these two vector spaces, the linear map A is defined such that if I add two vectors first and then I apply A, it's equivalent of first applying A and then applying A to V1, then applying A to V2, and then adding the sum. But you see here the colors are different because when I acted from V, I went to another map, M. Okay. Sorry, it's not correct what I said. When I acted on elements of V by A, I went to another space, which is W. Okay, so everything here in purple belongs to W. The same here, if I have some scalar and I act on something, okay, in V, and then I eat it by the A, I go to the V, I get the same value as if I ate something in V and went to W first and then apply the scalar multiplication with whatever group that W, so whatever operation that W had. Usually you're introduced to these two, okay, conditions in one written like this. Okay, so you're all familiar with this. This is the condition of being a linear map. Okay, okay. So this is just a shorthand notation. You see how much this, okay, notation eats or just like assumes between the vector spaces and so on that's underlying this. But this is more precise. If you know which vector spaces you're talking about, you can always write it like this. Okay. The set of all linear maps is itself another vector space that we discussed, and we call it L of V, okay, comma W. I think last time we introduced it with a semicolon. Okay, I'm just going to correct the slides in this. Any questions so far? The set of? Yes? The set K is already there. It's a field. It's not enough to have here a set, okay, to define a vector space. We need to define a vector space over a field, okay? And W in the field of K. Yes, exactly. Yeah, that's a good point. Yes. So here we assume that V and W are vector spaces over the same field. Okay. I'm not sure if you can even define like one vector space over a field and another vector space over another field. We won't need that. This is like too mathematical and too general. We don't need that operation. Okay. Linear maps. So what are, if we have an example of a linear map that goes from Rn as a vector space to Rm as another vector space, then you can show, okay, this is something that you can show, take it for now for granted, that any linear map, okay, anything that would act on an element of V, and we say that this is a linear map, it has to have this form, okay? The first, so A of V, okay, let's say that V is an Rn, then A of V would be an Rm, right? So it would have M components, right? M, not components, but M items. It's a tuple, it's an M tuple, okay? So we have M real numbers. The first real number is calculated by this. So it's a summation over I by multiplying some A multiplied by the first value or the first component of the V, and so on and so forth. You know this by heart, okay? And you've all seen it before on this side, written this way in components, okay? So you always think of the A in terms of its matrix representation. So if I tell you A itself, how do you think of it as a linear map? You tell me I know that it's an M by N matrix. It's just M columns and M rows and N columns of some numbers. These numbers are whatever components that go into this definition. Okay? And in this case, okay, just in this case, the set of all linear maps that go from Rn to Rm is what we call the set of matrices of m by n, m rows by n columns. Okay. I'll give you another example. So this is something I didn't talk about last time, but maybe it will make it just to distinguish, okay, how what is this idea of a linear map? I'm going to show you a map between Rn and Rm that's not linear. Okay, that does not satisfy the conditions we discussed. Consider this map psi that goes from Rn to Rm, and it's defined like this. It's very similar to what we had before. Okay, it's very hard to read it like this, and you want some time and want to expand it on a couple of papers, this is how you might think of it. Okay, so this kind of map is not linear. It's a map between Rn and Rm. Okay, but it's not linear. This is a type of map that's known as an affine map. Okay, and the reason why it's not linear is because it does not satisfy this condition. I'm going to go back to show you the condition first. So you see this condition. This condition says the following, that this condition has some implication that's very important. It says that if I choose the zero element, here, then what should A map U to? If I choose the zero element of Rn, I should be mapped to the zero element of Rm, exactly. So the zero element, or the identity element of the vector space V, should be mapped to the identity element of the vector space, okay, W. This is what this condition says. If you just want to prove it by math, you can check this. Okay, if psi is given by, again, in matrix multiplication between quotes, A multiplied by V plus some offset B. Okay, so B is an M vector, A is an M by N vector, and V is an N vector. Okay, does this sound familiar? A itself. Okay, so here I'm using. Okay, let me go back a little bit. A is the name of the map. A is the name of the map. You're used to think of A as this bunch of numbers set together. We're going to give it another name later on, or at least another notation to differentiate between them. But if you're talking about the map that goes from this space to that space, we call it A. It eats something in here, and A of V would give you something in there. Exactly in the same notation that we used to find map before. Okay. The A in the summation, these A's, these are real numbers. Yes, exactly. So you see here, each Aij, for I belong, that I goes from 1 to N, and J goes from 1 to M, Aij is an R. So A11 is an R, A12 is an R, A13 up to, okay, and so on.
Function and the map.
Function and map are two different names for the same thing. So a map and a function are the same. But the matrix representation of this map, of this linear map, something else. Okay.
About linear maps and affine maps, they are not necessarily opposite. Where we have like all maps that are not affine that need to be linear.
No. Just two names for different things. A linear map is what satisfies these conditions. If you take the special case of Rn and Rm, they have to have this form. This is something I'm not going to prove. Okay, you can check it out. They must have this form. In other words, I need to write it like a matrix multiplied by a vector in the way that you know it. And this is why linear algebra was all about this stuff, because it's talking about linear maps. Affine maps are different. They're not nonlinear. Okay, there is nothing called here nonlinear map. We didn't talk about any nonlinearity here, but it's not linear. What it is, it's not linear map from Rn to Rm. That's it. So it's just another example. It's one example of something that's not linear. It's a map between two vector spaces, but it's not linear. The reason this check down there is because if I, again, plug in here some scalar multiplied by V, okay, then the result would be A multiplied by some scalar, psi of some scalar multiplied by V is equal to A that eats this scalar multiplied by V plus some B. We know that A itself is a linear map, so we can take the scalar out. So we take the scalar out from the A of V plus B. If you check this guy, it's not equivalent to psi multiplied by, sorry, lambda multiplied by psi that eats the v. Because this was one of the conditions for the map to be linear. Okay, clear for everyone? Okay. If you look at it at your own pace and write it down, okay, it will be hopefully, inshallah, clear.
How can you like represent a map, non-linear map, using a linear map?
It's not a linear map. It's not a non-linear map. It's a map that's not linear. Okay.
How can you guarantee that this right there, like this not linear map between those,
Okay.
I will give this linear map plus b?
It's because it's just by the definition. You see, I define psi to be part of it is linear, plus part of it is some offset. Yeah, it's in general. Yeah. I define psi to be like that. Okay. You can define psi to be anything. Again, you can maps between Rn and Rm are too general. Like the set of all maps. We're not talking about this, the set of all maps. What we were interested in before is linear maps, and they should be written like this. This is an example of a map between the two vector spaces, the same two vector spaces, but it's not linear. Okay. Any other question?
You said that the affine maps, they are like a superset of the linear maps. Since if we set the B to have all these elements to be zero on the real number.
Yes, you can think of it this way. Yeah, you can think of it this way. Yeah, we're going to be focusing on maps from this side again, just as an aside, okay? You've all seen something like this, right? In what setting?
Linear system.
No, not what I want to hint to. Neural networks, okay, that's right. But in terms of robotics, in the context of robotics, neural networks again, pardon. What? Forward kinematics? Yes, exactly. That's what I'm looking for. Homogeneous transformations, right? I'm not going to say anymore, but that's just as an outlook, okay, for later on. We're going to be using this later on. This is just one case. Yes, exactly. Okay. Yeah.
So last week, the vector spaces, you said something about the linear maps.
Yes. Yes. The set of linear maps, this guy, in general, has a vector space of its own. In general, yes, exactly. Yes, exactly. Then we gave an example of just some special subsets of this linear space that goes from V to W, and we said that these are called endomorphisms, these are called automorphisms, and we give some examples from last time, and we said, okay, that the linear maps and the endomorphisms, they both have a vector space structure, but automorphisms, we cannot give them a vector space structure, but they can give in a group structure, and the other two, vice versa. Okay, and we'll give some examples for that. Now, today we're going to be continuing on vector space theory. We're not going to be introducing a new space, okay, or a new category, just like when we talked about sets and groups and vector spaces. We're still going to be talking about vector spaces, but we're going to be talking about more stuff in vector spaces. So you can expect that if linear maps correspond to matrices that you all know, and vectors, okay, or elements of a vector space correspond to what the tuple of numbers that you're all familiar with, then these kind of stuff will also be familiar. And this is the pain of this lecture, okay? But again, let's introduce stuff abstractly, and then later on, we're gonna hopefully link it to what you know or confuse you more. This is an experiment, let's see. So the notion of a dual vector space, okay? So for every vector space, I can talk about a dual space, and we call it V star. So if this is a vector space, I can construct from it, or it already has. I don't need to give it an extra structure. It already has a dual vector space. So it's a dual space that's also another vector space, and it's very important in mechanics. And who here heard about covectors or dual spaces before? Okay, so you can imagine how. So this confirms the second point. It's completely overlooked, but it's extremely important. And if anything in this course that you're going to get out of it is this notion of duality. Okay. While an element of V is called a vector, elements of V star are called covectors. Okay. Another name for covector is called a one form or a linear functional, or a linear, not a linear map, but a linear functional. just as an outlook without any proof for now, but this was what we're going to be covering later. Velocity-like variable. So anything that's like velocity has a vector space structure, or as a vector. It's an element of a vector space. While force-like variables are covectors. Okay, doesn't make any sense right now, but maybe okay later on this will make sense. Now, what is the definition of a dual space? Okay. The definition of so let V be a vector space over the field K. The dual space to V is defined as the set of all linear maps that go from V to K. That's it. So K plus and scalar multiplication in this case is considered to be a vector space over itself. You remember we said linear spaces are defined between V and W. V should be a vector space and W should be a vector space. But we're writing here K, but K was a field, right? So if we can trivially define this field to be a vector space over itself. So it's like a field over a field becomes a vector space over itself. Okay. So this is just a trivial case. What we're going to be thinking about, again, we took two examples that are important of fields, right? Either the real numbers or the complex numbers. Nothing here will be complex in this course. So whenever we say in this case, we just mean the real numbers. An element of this space, so what we call a covector, okay, or a one form, what is it? It's a linear map that goes from V to K. Okay. You should be understanding this without, okay, so you should be understanding how to read this without understanding what it means. Because if you don't know how to read this so far, let me know so that I repeat it. If you don't understand it, that's okay. That's expected. You know how to read it? Okay, an example. If we talk about Rn as an example, this is the vector space we're interested in, and the field is the R. Okay? Of course, here I'm not saying what is the addition, the operations that come with this vector space and what are the operations that come with this field. You already know what we're talking about. Okay? This comes with vector multiplication, vector addition, and scalar multiplication. This comes with scalar and addition, the normal ones, you know. So when we say it like this, it's implicit. Okay, now you're a higher level from what you started at the beginning of the course. The dual space to Rn is what we're going to be calling Rn brackets star. So this is the name of it. It's a new space, and it consists of all linear maps that go from Rn to R. So it would eat a map, it would eat an element of Rn and send you to a real number. And they should have this form. Okay? They should have this form. Okay? And you're familiar with them in this setting. So from what you know about linear algebra, what is it that we're talking about here as a covector? What? No? Yeah. Row vectors, exactly. So what you're used to as a column vector, okay, is what we call here an element of Rn. What you're used to as a row vector, okay, of course, your row vectors are just, I take this column vector and I write it differently, right? No. Completely different object, okay? It's a completely different object. Why? Because with this dot that you know how to multiply rows by columns and so on, then if I give you this alpha written as a row vector, it can, between brackets, eat this vector and give you what in the end? Just one number, okay? This number is calculated by what? The first number of the phi, of the alpha multiplied by the first number of the v. These numbers, we're going to be seeing later on how to define them, plus the second number multiplied by the second number, plus, and so on, which is what this summation is saying. Question? Okay. So this is what a covector is. What we just wrote here, that a covector is a map. A covector is a map. Okay. But as a map, I can either think of it as a map or an element of a space, right? And it means the same thing. Right? So it is itself a map, okay? But I can think of it as an element of this set of maps, okay, or this space of maps. There is some notation. This is just a notation wise, okay? And it will be very helpful, and you find it again in textbooks all over the place. that if we want, there's another way that people write this alpha eating the V, which gives you in the end a real number, or a number that belongs, or a scalar that belongs to the field in general. They write it like this. They introduce something called the duality pairing that would eat one element of V star and another element of V and give you in the end this number like this. It's just another notation for writing alpha that eats V. Okay? Because this one would be, you can understand that this is a useful notation because whenever we write stuff like this, okay, it will, okay, you will not be knowing, okay, is this a bracket? Is this a tuple? What are we doing here? So when we have more complicated expressions, this notation is usually annoying. This notation is nice. The first application of this notation is to define something called the dual of a linear map, abstractly. Okay. So you know what a linear map is? That would go from some vector space U to some vector space V. Then these are two K vector spaces. So this means that they are both vector spaces over the same field, K, U and V. Then the linear map A star, you see where does it go from? It goes from, not from U to V, but from the dual of V to the dual of U. So it's like A takes you from U to V, but A star takes you back from the dual of V to the dual of U. And it's defined implicitly. This is something, probably you've seen it in some papers before and maybe didn't understand it, but it's, when we say that, and it's an implicit definition, means that we're not writing it as something explicitly. It's just, if this map satisfies this, then this is its definition. Okay. And it's defined as follows. If you give me any element U of the space, of the vector space U, and any element alpha of the dual vector space V star, then A star, okay, takes an element in V star. Okay, so it will eat an element, it will eat the element phi. Okay, what is the result? It will be an element in U star, okay, because A star ate an element in V star, which is the alpha, gave you an element in U star. An element in U star can be paired by this pairing with an element of, an element in U star can be paired with an element of U. So if I choose any U and pair these two together, I get the same result as first taking the pairing between alpha and A acting on U, because U lives in capital U. When A eats U, I go to V. And if I have an element in V, I can pair it with an element in V star, which is the alpha. No, not the composition. The what? The inverse of? Good question. If A goes from U to V, and it's a linear map, you cannot, in general, define its inverse. It has to be another condition. What's the condition for A to have an inverse? It has to be a bijection. What is the name of the bijection that's also a linear map? A linear isomorphism, exactly. So if A is a linear isomorphism, then its inverse would go from V to U. It's not the same. Is V star the same as V? No, in general. Is U star the same as U? No, in general. You see, so they are different maps. What? Okay, you're trying to link it something. Did we talk about something called the pseudo inverse here? No. Okay.
What is equality here? What does it mean here? Equality sign.
Very good question. So, what if I take the pairing here between an element of V star and V? Where do I go? A K, which is R, for example. If I pair an element between U and U star, where do I go? The same space, right? The same field. These two numbers will be the same. That's what this means. Okay. What? Yeah.
case scenario, let's assume we're talking about a set of linear maps.
Set of linear maps. Okay.
That takes the form Rm cross n.
Okay. Yes. Okay.
Then this Rn.
You're going in a nice direction, but you're gonna get your mind. Okay. Wait. Don't think about it. Okay. I know you're right. What? Okay. What Muhammad's question is the following. Let's assume that V is a matrix. What would be? Okay, so let's go back to this example. So if V is a matrix, what is the covector of a matrix, right? If V is okay, here is Rn times M. What would be the corresponding linear maps that would eat this map? I'm not going to tell you the answer so that you don't go on in rounds. It exists, okay, but it's not something that you can at least now get your head around it, okay? This is the problem. Multiply it. This is the problem. Your minds are hardwired and thinking in terms of linear algebra, and that's the problem. Okay. Hopefully by the end of today, you're gonna have some extra tool that will help you in this question, but not necessarily.
What is its story? Instead, in the duality, like it is the set of all linear maps between, for example, S star is a set of all linear maps between U and V in the star.
This example. No, that's not what this is. Check here the definition. Again, let's read it. Let A be a map from U to V, be a linear map between the K vector spaces U and V. Then the linear map, so this is one linear map, A star, defined by this condition, is called the dual of the map A. So A is a map, and A star is a map here. We're not talking about sets of maps. V star, okay, that's a good question. V star is the dual of this, and this guy is the dual of that. What does the dual mean? We go back. The dual of a space means the set of all linear maps from V to the field. Okay, I can repeat it again and again, but I'm not going to give any extra information than that. Okay, you can have the video, you can rewind it all night long. Okay, there's no extra information. I'm sure you're not satisfied, but that's okay. Okay. What? One more question. Yeah. This one. Yes. That's right. If A star satisfies this, it's called the dual map.
Does it?
It's
Does it
not.
always exist?
Again, if you ask these questions, then okay, it's like we need to formally prove that for all linear maps it doesn't exist. You see, it's just the definition here. If you have some A star that goes from these spaces that are dual to these spaces in this order and satisfies this condition, it's called like that. It's just a definition. So this is the definition, and this is the definition, and even this is a definition. You see, these are all defined like that. Okay. Wait. Tensor spaces. Who here heard about tensors before? Okay. Who understands tensors? Okay, good. Okay. Let me confuse you even more on what you even know. What is a tensor? A tensor is simply a multilinear map. And what we're going to be introducing here, they are maps that would eat V star. It would eat P elements from V star. Okay, not P elements from the same V star. It would eat, it would eat from, it would eat P elements from V star. That's correct. Okay, P elements from V star and Q elements from V. So it's a multilinear map. Okay, and it would send you where? To K. Okay. So T is a map. So T by itself is a map. This is what's called a tensor. It's a map that would eat P covectors and Q vectors. Make sense? Is it related to what you learned? Of course not. Okay. So the term multilinear here means that in each of these entries, I have the linearity condition that we introduced, right? So if I have two elements plus and multiplied by some scalar, to satisfy the same condition we're talking about. This is what multilinear means. The rank of a tensor is simply the sum of P and Q. Okay, so when I say a first order tensor, what do we mean here? The rank is 1, and then P and Q needs to be what? 1, 0 or 0, 1, right? If I say a second order tensor, then can I be 1, 1, 0, 2, or 2, 0, right? That's exactly what this is. So the tensors can go up to, again, 100 by 100. So we're not interested in these. Usually, okay, what appears here in mathematics, at least in mechanics, what we're interested in, I would say, are 0, 1, 1, 0, 1, 1 tensors, 0, 2 tensors, 2, 0 tensors, and maybe some third order tensors, but that's it. Okay. 0, 1 tensor, again, if you go back to the definition, a 0, 1 tensor is a map that would eat 0 covectors and 1 vector going to K. What is that? What we introduced? Simply covectors, right? So in this case, a 0, 1 tensor is a covector. What is a 1, 0 tensor? Okay, this is something we're not going to be proving, and it's not in general for all vector spaces true, but for finite dimensional vector spaces, it's true. Let's go back to here. So we said that V star is a vector space itself, right? Which means I can define the dual of V star. What do you think the dual of V star is? It's the map from all V stars to K, and you can show that it's equal to V. Okay. So the dual of the dual is V. Okay. Another example just to show you what that means. If the dual of the column vector is a row vector, then what is the dual of the row vector? Column vector. Okay. So this is not in general, like, not as easy as this in general, but abstractly this holds for all vector spaces that are finite dimensional. So a 1, 0 tensor that is some vector, some covector that gives you a real number, okay, is an example of a vector. 1, 1 tensors take one element from here, one element from here, give you a K. A 0, 2 tensor, which are called bilinear maps, it's one element of V and one element of V gives you a K. 2, 0 tensor, which are not very popular, it's two elements of V star and gives you one K in the end. Again, let's make it, okay, let's combine stuff. The set of all PQ tensors on V will be denoted by this symbol. Has anyone seen this symbol in some paper before? Okay. And it has a vector space structure. So the set of all tensor fields can be made into a vector space. Okay. Which means that if I have two tensors, I can add them together. What a vector space structure, if you always want to remind it with something very easy to think about. If something has a vector space structure, this means if I take two elements of them, I can add them together by whatever operation this has and get another vector. Just like when you have an n tuple and an n tuple, you add them together, you get an n tuple. So this is a vector space because it has a vector space structure. If there is something that there's some set that you add two elements of them and you don't get another element in the same space, it doesn't have a vector space structure. This is a very easy check to one of the conditions that we need to satisfy. So the sum of two tensors is another tensor. Okay? The sum of two 0, 2 tensors is another 0, 2 tensor. The sum of two 1, 0 tensors is another 1, 0 tensor, and so on and so forth. Okay, this is what this means in a nutshell. There was a question here.
Order the 0, 1, is it supposed to be the tensor vector or both tensor? Because from the equation you gave earlier,
Yeah.
yeah, the covector comes first.
Yes.
Or we go to the next one.
So you're saying about 1, 0. So 1, 0 would eat V star and go to K. And 0, 1 would eat a V and go to K, right? 0, 1 would eat a V and go to K. 1, 0 would eat a V star and go to K. Consistent, okay? Yeah. This one? Yes. 1, 1 tensors are called linear maps. 0 2 tensors are called bilinear maps. Okay? Don't ask if I don't say it, otherwise you're going to get confused. Okay. So you've seen tensors, or you've seen all of these elements that we abstractly introduced on purpose. You've all seen them in components. Okay. I'm pretty sure you've never been introduced to them in this abstract way, but you've all seen them in components. Okay. You all know that a linear map is some matrix with some order. You all know that a vector looks like something as a row column vector. Now I show that a covector is something you can write as a row vector and so on. So these are called components, but you can only write these abstract concepts or these abstract objects in components once you choose a basis. Okay. What? That's a good point. So what is the basis? The basis is, these three, a frame, right? You've all seen them as a frame, right? This direction and this direction and that direction. And I can write any vector in terms of these, okay? This is what a basis is, what you know about. Formally, what is a basis? Again, a definition. Let V be a vector space. A basis S for a vector space V is a collection of vectors in V. That's it. So a collection of vectors in V, we can call them a basis if they satisfy these two conditions. The first one, they should be linearly independent from each other. The second one, they should be generating the same vector space we took them from. What does this mean? The first condition, linear independence, means the following. This is the formal definition, but you know them again in another way. A set S, which is a subset of V, is a collection of vectors that are linearly independent if, so this is the condition, for every finite subset, okay, I take them, the equality that if I sum for some constant Ci, so Ci, Ci1, C2, C3, up to Ck, and I multiply C1 by E1. The E1 was a vector, okay, from V. So E1 is a vector, up to Ek are vectors. If I multiply C1 by this vector, plus C2 by the second vector, C3 by this third vector, and I get 0, if I do that, this equality implies, or this equality can only hold if the numbers C1, C2, C3, up to Ck are each one of them is 0. So this is what linear independence means. You all have seen this before, okay? Definitely in linear algebra. And you had checks that you can do. If I give you a number of vectors of Rn, there were some checks that you can do to make sure that they are linearly independent or not. What was this check? There was some procedure. What was it? So if I give you 3 vectors in R3, how can you make sure 3 column vectors in R3, how can you make sure that they are linearly independent? Form? Okay. Take the determinant of what? These are vectors.
Okay.
I combine them into a matrix, then I take the determinant, and then if it's 0, then they are not linearly independent. Okay, or in other words, they are linearly dependent. If it's not equal to 0, they are linearly independent. Seen that before? So this is what this says. What is the second condition? That they should generate V. If a set S that generates a vector space V, if every vector in V, I can write it as a linear combination for some constants, okay, in terms of E1, E2, and E3 up to Ek. And in this case, we usually say, if this is the case, we write that V is spanned by S. And usually we introduce the field that this is a vector space over just to be consistent. Have you seen this before also? Let's take an example. So this is where we turn to the writing whiteboard. Let's see. Going into Blackboard. Let's write this guy. Yeah. Oh, they are all vectors of some vector space, not of the same vector space. Yes, that's correct.
Our general intuition about linear algebra and the way the multiplication work and addition work.
Linear algebra is only the case Rn. Vector space Rn, that's it. So it's not generalizable. So what you learned in linear algebra is only for the case that vector spaces are a tuple of numbers, Rn or Rm. And they have even more structure than what a vector space should have. For example, we didn't talk about vector products, dot product. Okay, this is more structured than what a vector space has. So we didn't talk about it. Vector cross product, extra structure, we didn't talk about it. So we're talking only about vector addition, scalar multiplication. This is what makes a vector space, and everything else that comes with it. Okay.
It seems like still we are talking about a small subset, even if we were to take the different sets of the different vectors as a single set.
Then wait till this example, and you're gonna see. Okay. Let's take some examples for bases. Let's take first V to be R2. So the plane. You all know, okay, and you even take it without thinking that if you think of R2 as something like this, right? But it extends infinitely, okay, right and left and up and down. Right? You all think of this guy and that guy, E1 and E2, and you say that these are bases for R2, right? Why is that? First, they are linearly independent. How can we write them? How do we represent them by numbers? Themselves, these are the standard bases. They are called the standard bases. So E1 is written like this: 1 in the first direction and 0 in the other direction, while E2 is defined like, so this is defined as 0 and 1. So 0 in the first direction and 1 in the second direction. They are what they are because of their definition. So these two bases, and if I give you another vector like this, so this vector V, okay, so E1 lives in the vector space V, which is in this case R2. E2 lives in the vector space, sorry, V, which is R2, and also V here lives in the vector space V, which is R2 in this case. And you know that I can represent this vector like this. I can write it as some constant some constant V1 multiplied by E1 plus another constant V2 multiplied by E2. And just to make sure that we differentiate here on the board that what is a vector and what is a number, what's a constant, usually we would give these some hat, okay? We'd call this a hat, and then writing it like this is what you think of V1 and V2. There's another way of writing V, which is, again, maybe what you're more familiar with is writing V as V1 and V2, right? So this is what you know, but you've probably definitely, I'm pretty sure you've seen this before, right? But not used it. Okay. What is the difference between this, okay, and notation-wise? They both mean the same thing. They both are a representation of the same vector. What are these two? What is the difference between these two, notational-wise? So what is extra information here that's not in here? The bases themselves, exactly. So here we write the bases explicitly, but here we implicitly, we think, okay, we assume that the reader knows that we mean that is V1 in this E1 direction and another E2 direction. So this is this case. You can extend it to R3 very easily, right? Is that clear? Now I'll give you another example of another vector space. This vector space is called SON, small s, small o, brackets n. N here represents the dimension. Okay, it can be it can be 2, 3. We're interested only in 2 and 3. Okay, but in general can be anything. Okay, before saying how's this a vector space, I need to define it. So I'm going to define SON as the set of all elements that live in R3 by 3. So they all have 3 by 3 matrices that they love. But they have a condition that when I take the transpose of this X, I get the minus. So these are the set of what? What are they called? Set of what? Skew-symmetric matrices, exactly. So this is the set of n-dimensional skew-symmetric matrices. You can show, okay, this is in general true, that when we have SO2, okay, so elements of SO2 should always have this format, okay, because of this condition. Okay, I'm not gonna show it. Maybe if I find it's easy that you can do it yourself, I might put it in the homework. But again, you can show it for yourself that diagonal elements of this set will always have 0, and off-diagonal elements should always be related to each other. Okay, so if this is A here, then this is minus A. Should always be this case. In 3 dimensions, so SO3, again, you have also diagonal elements that are 0, and then you have here, you have 3 numbers that correspond to this, and this, if this is A1, this would be minus A1. If this is A2, this would be minus A2. If this is A3, this would be minus A3. So any element of SO3 would have this form. Any element of SO2 would have this form. Yes. Yeah, that's absolutely correct. Yes, thank you very much. N by N, that's correct. N by N. Thank you, Farouk. Okay, so this is a vector space. Can we represent them by a basis? Yeah, the definition says yes. What is the basis of SO2? Okay, we need something that we can write any element of SO2 as some number multiplied by this element of SO2. What do you think this element is? So the basis here, okay, would consist of only one element that has the shape like this. So this is the basis for SO2. You all agree? Okay. Because any element of SO2, I can multiply this matrix that's also skew-symmetric. So this is important. You see, E1 is skew-symmetric matrix, so it's an element of SO2. I can multiply it by one scalar, and actually this is the scalar that's either here or minus the scalar that's here, and then I get an element of SO2. Let's do the same here for SO3. So the basis E of this space, E1 and E2 and E3, would correspond to this set that would have 3 vectors of this vector space. The first one looks like this. The second one looks like this. And the third one looks like this. Take a look at it to digest it. Sorry? You mean all line entries are 0? Yes, it has it. Because you can construct it by multiplying these 3 together by 0, right? So, or this one by 0. If you multiply it by 0, you get the 0 matrix. The 0 matrix has to be part of these vector spaces. Otherwise, they won't be vector space in the first place, right? This is exactly, that's the identity element. Very precise. Yes. Yep.
Then why is it necessary to that?
This is again something that any skew-symmetric matrix of dimension n would have this property. Okay, because of Muhammad, I'm gonna put it in that assignment. Okay, then you have to prove it for yourself. Okay, or ChatGPT will give it to you very easily. Okay, but again, you're gonna work it out. Okay, you just need to work it out, and okay, you're gonna get 1,000 reals if you can find a skew symmetric matrix that doesn't have this form. Okay. Yes.
So we're talking about the diagonal elements.
Yeah.
So diagonal elements can be left diagonal or right diagonal. So is there like are we going to impose like a condition? Are we talking about the right diagonal or left diagonal?
There are only one diagonal elements, which is these. How do you define the diagonal elements? First row, first column, second row, second column, right? There isn't any other way. Okay. Any other questions? Okay. Now let's go to another side. What are the components? Now, components. So the components of a vector, how are the components of a vector defined? So if I give you V that belongs to vector space capital V, and I tell you also that I have the basis E1 up to En, okay? So here we assume that V has a dimension of n. We haven't talked about what the dimension is, but again, you know intuitively what it is. If this is an element of a vector space, so V is a vector space, this is a basis for V, then there exists some constants. These constants are V1 up to Vn, index up. Okay, so this is just an index. It's not a exponent, so it's not V multiplied, V1 and V2 is V squared and so on. These are just indices, names of these, okay, constants. Each one of these belongs to R. So assumed here that V is an R vector space, okay, which is what we're going to be doing from now on. These exist such that V can always be written as V1 multiplied by E1 plus Vn multiplied by En. Okay. Or in other words, I have this summation of I that goes from 1 up to n multiplied by V index up I, E index up, index down I. And these components, so these guys, so these are called the components of V in basis E1 up to En. Clear for everyone? Make sense? Now we're going to introduce something called the Einstein summation convention. Okay, we're going to be having these guys all over the place, and this is where it's a convention that's associated to Einstein, that if we have an index up and an index down, this will imply that there's some sort of summation. Okay, so the Einstein summation convention, simply instead of writing all of these summations over the place, and then we can have tensor fields that will have more okay, these summations, it's just as a shorthand notation. So it's a notation wise that we can write this as V E I up, E I down. Because we have one index up and one index down, this implies that we are summing over I. So this notation is equivalent to that notation, okay? And we're going to be using it, okay, regularly. Okay, does that bother anyone? Okay. If we're talking about the components of a vector, what else can we talk about? What else can we define with these components, similar to these components? We define vectors abstractly, and these are the components of a vector, right? What else can we define? Components of a covector. If a vector is given like this, we can define the components of a covector. But before defining what the components of a covector is, we need to introduce the dual basis. Okay. So if the set E1 up to En all of them have index down, is a basis for V. Then another set, E index up, E index up, is a basis for V star. Of course. Yeah, they definitely need to be in a relationship. What is this relation? The condition is that EI should be equal to 1, and EI EJ should be equal to 0. In other words, okay, we can summarize this. Okay, so what this says is the following. If I take the first covector from here and I make it eat the first vector from here, again, a covector that eats a vector returns what? A number, a scalar, right? If you remember what were covectors, a covector alpha is a map that goes from V to R, if V is a R vector space. So alpha eats V and goes to R, then I can make this eat that guy. Okay? So I can write it also in terms of the duality product. And if you remember, we said that if E1 acts on E1, then I get 1. If E2 acts on E2, I get 2. If E1 acts on E2, I get 0, and so on. So we can write this in another way, okay, in a compact form. By writing this EIJ, okay, so the pairing between these two is equal to the Dirac delta function, where this is equal to either 1 if I is equal to J, and 0 if I is not equal to J. Just to, okay, satisfy your eagerness to think in terms of linear algebra. If we said that if we have Rn, if V is equal to R, let's take R3 for example. So the bases for R3 are 1, 0, 0, 0, 1, 0, and 0, 0, 1. You all know what this means? Oops.
Question, please, Prof.
What?
Question. What
No, wait first. Wait, 1 second. So, sorry. And then what would be the dual basis? Can you guess? 1, 0, 0 written as a row vector. And E2 is 0, 1, 0 written as a covector. And E3 is 0, 0, 1 written as, okay, like that. If you multiply these guys by that guys and you put them in sort of some matrix, you're going to get actually, this is the identity matrix. And this is, by the way, this is just some sort of writing the identity matrix. Farouk, the question.
What it would be called EI and E subscript I? Are you using the Einstein notation?
Yes, yes, I did it implicitly. Yes, that's right. Yeah.
Then we should not have 1. 1 is the scalar.
You're summing between I and, again, each one of these is already has its components of its own. You see? Okay. Let me, okay, this will be part of the homework, okay, but I'm just gonna give you the end results for now because we only have 5 minutes left. Let me give you the end results so that you see where we're going. What are the components? What? Okay, people will start beating you, so don't say that in public. Okay, so components of linear maps. Okay, so again, so just to summarize what we mentioned, we said that vectors can be written like this: V, I, E, I, and covectors can be written as alpha I, E, I, right? In the same way, in the same logic. What do you think about linear maps? Okay. Linear maps, we said that the components of linear maps, A that eats V and go to, sorry, it eats V and goes, sorry, it eats two Vs. Sorry, 1 second. So linear maps that go from V to V. Okay, linear maps that go from V to V. What would be their components? How do we write them? You're going to find that we can write them in the following notation. A, it would have one index up, another index down, and it will have this to be EI. And this will be something called the tensor product. We're going to see it next time, inshallah. And EJ like that. What about bilinear forms? So bilinear forms, okay, we said that it's a map from V to R. Okay. And another way of writing this, we said that linear maps are a map from this guy to that guy to R, without saying what's the relation between these two. This will be done next time, inshallah. But bilinear forms would have B, I, J, E, I, E, J. You see what we're doing? Okay. So in terms of matrices, what is the difference between these matrices and that matrix? Nothing. Okay, nothing. Because if I give you some bunch of numbers and I tell you write them in a matrix form, you're going to take the A11, A12, A21, A22, or you take a B11, B12, B21, B22. You all agree? If I give you 4 numbers in here and 4 numbers in here, you would write them in matrices like that. But does this matrix, if I give you just the matrix, can you identify whether it's a linear map or a bilinear map? You cannot. And this is the main problem of matrices. If I give you a vector, a bunch of numbers, can you identify whether it's a vector or covector? You also cannot. How can we identify whether a given object belongs to whether it's a vector or covector, a linear map or a bilinear map or any kind of tensor? This is the answer that we're going to be doing next time, inshallah. Okay? Any questions? Clear? Okay. I'm sure it's not clear. It's not 100% clear. Okay, so okay. But at least the definitions, okay, we're going to be using all of these later on. Okay? So let's stop here.